Welcome to the 10th lecture on digital simulation. In this video, we will discuss how to solve a system of nonlinear equations using Newton-Raphson method and what are the factors affecting the total computation time requirement and what are the different convergence issues associated with this method. So first, let us consider a system of nonlinear equations. Suppose there are n equations. We have to solve a system of n equations in n variables. So the variables are x1, x2 up to xn. So the first equation is say f1 of a function f1 of x1, x2 up to xn equal to 0. This is the first equation. Then second equation is f2 of x1, x2 etc. up to xn equal to 0. Like that there are n equations. So we need to solve a system of nonlinear equations. So in Newton-Raphson method, we will start with an initial guess. Suppose x of 0 denotes the initial guess to the problem. x1 of 0 is the initial value or initial guess for the variable x1. x2 of 0 is the initial guess for variable x2. Like that, there are n values and it is arranged as a column vector that forms x of 0, our initial guess vector. Now, before starting the iterative procedure, first we have to check whether this initial guess is very close to the solution. If it is acceptably close to the solution, then we can stop the process at this point itself. There is no need to go for an iterative procedure if the initial guess itself is close to the solution. So in order to check whether the initial guess is very close to the solution, we have to evaluate the function values at the initial guess. So first we have to evaluate f1 at x of 0. Then evaluate f2 at x of 0. Like that, evaluate all the function values fn at x of 0. Then take the sum of the squares of these values and take the square root of this. So this whole thing is known as 2 norm of this function. So it is denoted as like this. So the 2 norm is defined as sigma of fi square, where I going from 1 to n, and square root of this quantity. That is the 2 norm. If this 2 norm is acceptably close to 0, then we can infer that the x of 0 initial guess is acceptably close to the solution, actual solution, and we can take it as a root or a solution to the problem. If this value f 2 norm of f is not close to 0, then we have to go for the Newton-Raphson procedure. If the 2 norm is less than epsilon, a tolerance value, then we can accept the current solution. Otherwise, we have to go for the first iteration. So suppose x of 1 is a better update to the initial guess, and x of 1 is acceptably close to the root. Then f1 of x of 1 will be close to 0. So that is written here. X of 1 is, there are n values, x1 of 0 plus delta x1 of 0, comma x2 of 0 plus delta x2 of 0, like that xn of 0 plus delta xn of 0. This is acceptably close to 0. Like that there are n equations. Now these equations can be expanded using Taylor series. So what we are doing is, we started with an initial guess x of 0, and we are updating this x of 0 by an increment delta x of 0, and we are assuming that this new value x of 1 is acceptably close to the solution, actual solution. Then the function will approach 0 at x of 1. So that is written here. Then using Taylor series, we can expand the previous equations like this. So f1 of x1 of 0 plus delta x1 of 0 comma x2 of 0 plus delta x2 of 0, like that. Xn of 0 plus delta xn of 0. This can be expanded as f1 of x1 0 comma x2 0 up to xn 0 plus the partial derivative of f1 with respect to x1 multiplied by delta x1 plus partial derivative of f1 with respect to x2 multiplied by delta x2, like that up to the nth partial derivative here, dou f1 by dou xn into delta xn of 0, like that. Expand all other functions f2 etc up to fn. So we will get the system of equations shown in equation number 5. Now we can arrange this system as in matrix form. So in matrix form, I have arranged these coefficients of delta x1, delta x2 as a matrix here. So that matrix has elements dou f1 by dou x1, dou f1 by dou x2, dou f1 by dou x3, like that up to dou f1 by dou xn in the first row. So the remaining rows can be filled like this. It is multiplied by the update vector delta x1 of 0, delta x2 of 0, etc. up to delta xn of 0. This is coming from here. Delta x1 0, delta x2 0, etc. up to delta xn 0. This is equal to, you can bring this these terms to the right hand side. So it will become minus of f of 0. So minus of f1 of 0, minus of f1, f2 of x1 of 0, like that. So now this is like ax equal to b, a system of linear equations. So this can be solved using either Gaussian elimination or Gauss-Jordan method. So the previous system can be written like this. This matrix is known as Jacobian matrix, and it is denoted by J. And this matrix is denoted as delta x of 0, and this one is minus f of 0. So in matrix form we can write it like this. J delta x of 0 is equal to minus f of 0. So delta x of 0 is equal to minus j inverse into f of 0. Now we can add this correction vector to our initial guess x of 1 to initial guess x of 0 to get the updated value x of 1. So x of 1 will be x of 0 plus delta x of 0. This updated vector x of 1 becomes the initial guess for the next solution. So this process is continued till the convergence criterion is satisfied. The convergence criterion we have already seen in the beginning. We have to check the 2 norm of the function, whether it is less than or less than a tolerance band. If it is less than a very small value epsilon, then we can stop the iterations. Otherwise, we have to go for the next iteration. So now let us see what are the factors affecting the computation time of the Newton-Raphson method. The CPU time depends on 2 factors: the total number of Newton-Raphson iterations required for attaining convergence and the time taken for one iteration. So the number of iterations and the time taken for one iteration. So let us look at these factors one by one. So if you look at the number of Newton-Raphson iterations required, so the number of Newton-Raphson iterations required depends on the initial guess. So if you select if you start with a proper initial guess which is acceptably close to the root, then you will reach the convergence. You can satisfy the convergence criteria in minimum number of iterations. So if you are not starting with a proper initial guess, the Newton-Raphson procedure may not converge, or it may take more number of iterations. So if an appropriate initial guess is used, then the Newton-Raphson method usually converges in 4 to 6 iterations. That is a typical range. So the number of iterations required depends on the selection of initial guess. Then the second factor was time taken for one iteration. So in one iteration we are solving the linear system of equations. J into delta x of 0 is equal to minus f of 0. So Jacobian is also evaluated at the using the initial conditions or the initial guess. So the Jacobian has to be evaluated and the right hand side vector has to be evaluated for solving this linear system of equations. So these two factors, the evaluation of Jacobian and the right hand side vector, determines the time taken for one iteration. Then we have to solve this system to get the correction vector. So the time required for evaluation of Jacobian and this right hand side vector will increase as the size of the system increases. So the CPU time required for the solution of the linear system increases more rapidly as the Jacobian size increases. Okay, so these two factors illustrate that the circuit simulator, the performance of the circuit simulator will be governed by the performance of the linear equation solver used in that. So the time required for evaluation of this Jacobian and the right hand side vector will grow linearly as the size of the system increases, and the CPU time required for solving this linear system usually increases at a much faster rate. So sorry, this is n raised to 1.5. okay, here this time increases directly proportional to n, size of the system. Suppose the size of the system is n by n, size of the Jacobian is n by n, then the time required for evaluation of Jacobian and right hand side vector increases linearly with this size, whereas the time required for the solution of linear system increases proportional to n to the power 1.5, slightly larger than this proportionality. So a proper linear equation solver is required for getting a faster solution. Now coming to the factors affecting the rate of convergence or convergence issues in Newton-Raphson method. In a single variable, we will consider the single variable Newton-Raphson method. So in the previous class, we saw that xn plus 1 will be equal to xn minus f of xn by f dash xn. So generally, in this quantity x minus f of x by f dash x, let us define it as g of x. Okay, so g of x is defined as x minus fx by f dash x. So xn plus 1 is xn plus delta of x of n. So this quantity xn plus delta of xn is actually g of xn, because g of xn is x of n minus f of x of n by f dash of x of n. Okay, this is same as x of n plus 1. X of n plus 1 is x of n minus f of xn by f dash xn. That is also denoted as g of x of n. Now we can write g of x as g of x can be written as g of r plus x minus r. So this can be expanded using Taylor series, g of r plus g dash of r into x minus r plus g double dash of r by 2 factorial into x minus r square. So that is written here. So there will be infinite number of terms. So if we truncate this series at the second after the third term, if we truncate this series after the third term, and this instead of in order to account for that, we will write it as g dash of psi by 2 into x minus of r square, where psi lies between x and r. Now what is f of r? F of r is the root of the problem, f of x equal to 0. So the root of this equation is r. So f of r will be 0, that is written here. Then what is g of r? G of r is r minus f of r by f dash r, because g of x is defined as x minus f of x by f dash x. So if you put x equal to r, it will be r minus f of r by f dash r. Then what is g dash of x? G dash of x is derivative of x is 1. Then apply calculate the derivative of this. So f of x by f dash x, derivative of f of x by f dash x is denominator into derivative of numerator is f dash x minus numerator into derivative of denominator. So that is written here. Here f dash of x square minus f of x into f double dash x divided by denominator square. So f dash x square. Now if you put x equal to r here, you can see that g dash of r will be 0 because g dash of r will be here, this is 1 minus f dash of r the whole square minus f of r into f double dash of r by f dash of r square. So here you can see f of r is 0. F of r is 0 from this equation number 14. So this term will vanish. So this is f dash r square by f dash r square. So it is 1. So 1 minus 1 will be 0. So g dash of r is 0. So in the previous equation, this term will now vanish. G dash of r will be 0. So that is updated here. So g of x becomes r plus g double dash of psi by 2 into x minus r square. So now g of x of n will be r plus g double dash of psi by 2 into, instead of x, substitute x of n minus r the whole square. Now g of xn is nothing but x of n plus 1 that we saw in the beginning. G of xn is nothing but x of n plus 1. So x of n plus 1 is equal to r plus g double dash of psi by 2 into x of n minus r square. So bring this r to the LHS. So x of n plus 1 minus r is equal to g double dash of psi by 2 into x of n minus r the whole square. Now this is a constant term. It can be written as k. So x of n plus 1 minus r is the error in the n plus 1 iteration. So epsilon n plus 1 is equal to k into x of n minus r is error in the nth iteration. So now you can see that error in the n plus 1th iteration will be square of the error in the nth iteration. So the error will drastically decrease with at an order of 2. So there is a quadratic convergence for Newton-Raphson method. So convergence is quadratic because error in successive iterations will decrease at a faster rate. Error in the third iteration will be proportional to square of the error in the second iteration. So similarly, error in the fourth iteration will be proportional to square of the error in the third iteration. So error will drastically come down to acceptably small value. So there will be a fast convergence compared to other methods. So the error goes down quadratically as x of n approaches the root. So the order of convergence of Newton-Raphson method is 2. The convergence is guaranteed only if the initial guess is sufficiently close to solution R. And there is a analytical result. If f of x multiplied by f double dash of x divided by f dash of x the whole square, if the absolute value of this is less than 1 in an interval about the solution, then the Newton-Raphson method will converge for an initial guess selected in that interval. So this can be proved using the previous expression. From this g dash of x we can prove that, but the derivation is not required here. So if this condition is satisfied for an interval about the solution R, then the and if you select the initial guess in that interval, then your Newton-Raphson method will converge for that initial guess. So let us take an example. Suppose we have to solve tan inverse of x equal to 0. This is a nonlinear equation. Suppose we start with an initial guess x equal to 1.5. Then if you do this Newton-Raphson procedure, you can see that the method will fail to converge. This is because this is not a good choice of initial guess. So the main point to remember is that Newton-Raphson method may fail to converge if you your initial guess is not properly selected. Now coming to damping in Newton-Raphson method. So sometimes the Newton-Raphson method fails to converge because the update delta x, we are calculating the value in the first iteration using initial guess plus update vector delta x. So if this update is not acceptable, if it is very large, then it may overcorrect the initial guess. So we may diverge away from the solution. So in such cases, the direction given by delta x may be correct, but the magnitude may not be correct. So in such cases, if we follow the direction only given by the Newton-Raphson method, but we use only a part of the correction delta x, then we have a better chance of approaching the solution. That is, we use only the polarity of delta x and the magnitude we will damp down. We will not use the exact magnitude of delta x, we will use only a fraction of that. So mathematically it becomes like this: x of n plus 1. In original Newton-Raphson method, x of n plus 1 is xn plus delta of xn. Okay. But in if you are using damping in Newton-Raphson method, you will multiply this update vector by a factor k. So this k, which is usually less than 1, is termed as damping factor. So this will improve the chances of convergence. But what are the effects of doing damping? Damping is used only if the standard Newton-Raphson method fails to converge. Otherwise, there is no need of doing damping. If the standard Newton-Raphson method fails to converge, you can use damping and try. A larger damping may slow down the process convergence significantly, and usually this damping is applied for the first two or three iterations, first few iterations. So this initial damping will bring our the new value close to the root, and later we can remove the damping so that it will converge quickly. So the initial damping will take the process close to the solution, and later undamped iterations without damping may bring the process close to the solution quickly. So that is the usual procedure. And what are the practical limits in using the Newton-Raphson method? Because we are using a computer to solve this system of nonlinear equations using Newton-Raphson method, the computer has a finite precision or resolution, so that will determine the accuracy of the solution. A double precision real number is represented by 64 bits. So 1 bit for sine, 11 bits for exponent, and 52 bits for mantissa. So it is a finite representation. There are finite number of bits available to represent the data. So due to that, there will be limitations in the smallest number that can be reached or the largest number that can be reached. So the smallest number in this case is 10 to the power minus 308, while the largest number is 10 to the power 308. So since we are not exactly reaching 0, the minimum number that we can represent is 10 to the power minus 308. Because of this limited precision, the number of numbers falling between successive discrete real numbers R1 and R2 will be rounded off to the nearest number. So this will introduce a round off error. So due to this finite precision of the computer that you are using to implement Newton-Raphson method, there will be a round off error. So the round of errors have a cascading effect in Gaussian elimination. If the round of errors in the first iteration, the one step of Gaussian elimination will propagate to the next rows. So there will be a cascading effect in Gaussian elimination. So the precision has a significant impact on the lowest value of norm that can be achieved. So the value of norm is what we are checking for reaching the convergence criteria. So the finite precision of the computer has an impact on the lowest value of norm that can be reached. And another observation is, if you scale the equations by a constant value, that will also has a major effect on the convergence behavior, and sometimes the equation may diverge. Okay, these are the important points regarding Newton-Raphson method to solve a system of nonlinear equations. Okay, thank you.